Hello, everybody. Last we left with having calculated the angles A and B and the distance, and after finding out angle A and B, we converted them into the initial course and final course. Then the next step in the question is to find out the vertex. So this was the question what I was doing with you last, and I had calculated the initial course, final course, and the distance. And the next step is to find out the vertex. I will continue with this question here. But before we go ahead with solving for vertex, we should know what is vertex and why do we need to calculate vertex. Now, vertex is the highest point reached by the great circle track closest to the pole. And as we know that all the circles what we draw, they will tend to curve towards the poles. So we should know what is the highest point the track is going to get closer to the poles in order to avoid latitudes. Higher latitudes associated with bad weather. We could find ice, have fog, bad visibility, strong winds. So the master may decide not to touch very high latitude what the track is taking me into. So latitudes are necessary to be found for finding out your highest latitude. And the second thing is about intermediate points. Now, when we talked about the higher latitude, and that is the reason that I had asked you to be using the pole on the higher side, because if you look at it here, I'm starting from 10 degrees south. It is going to turn towards the pole on either side, either this side or this side. And I'm starting from 10 and I'm going towards 47 north. So I'll take this curve here. So I'll be interested in the point on this curve rather than the curve which is going towards the south pole, because I'll definitely not be touching anything more than 10 degrees south on this course. So we are interested in knowing the highest point it will touch the poles. So that point could be somewhere on the track here. It may be outside. So, but we should be aware of it where it is lying, so that in case it is in the somewhere in between the triangle here, we should be able to avoid it. This intermediate points what I was talking to you about is now this great circle track. We know that we have to keep on altering our courses on and off with change of meridians, with change of longitudes, and that's not practical. So the master decides that he should go along the rhumb line track so that he can continue on one particular course for certain distance and then alter course, again continue for certain distance and alter course. So now what he has done, he has broken up this great circle in order to be following a course which is as close as possible to the great circle without having the inconvenience of altering courses on and off. Now he decides to alter course after a certain amount of longitudes. Like here he says from 10 degrees west. So he's already decided that from 17 degrees west to 10 degrees west he'll continue on one course. Then from 10 degrees west he'll go another 10 degrees, that is he'll go up to Greenwich meridian, and so on. Now he has already decided the longitude, but he is to find out what latitudes he should be altering his courses. So in order to calculate our latitudes, that is where we use the vertex. And calculation of intermediate points is going to be the next topic, so I'll leave it here. But before we go further up, let us just get an idea about how the great circle behaves great circle track behaves on the surface of the Earth. Now this is what I'm trying to show you, the Earth with its center and great circle passing through east and west. And this is your plane. I will request you to just visualize something like this. This is the plane of the equator which is passing. And how is this plane going? Along the screen of my computer here. And I've just taken some of these lines here to show it to you that these are the axes of the plane. Now, if I take 2 points on the surface of the Earth, and we know that I can draw at least one great circle through 2 points as long as they are not on the extreme diameters. So one circle is always possible. So I just draw one circle here. Of course, these diagrams are not depicting the way the thing should be going, because I could not make those curves like this. But all your tracks, whatever it is here, they'll be turning towards the pole and then going here. Similarly, going up and coming down here. So when we see this and try to visualize the plane of the great circle, they both having equator and this having the same center, it will be something like this. And these lines, what I'm showing is the axis of the great circle also. If you see here, this great circle is half above the plane of the equator and half below the plane of the equator. Being 360, that means 180 is up and 180 is down. And these 2 points, C and D, they are diametrically opposite and they are closest to the poles. Of course, other points are also diametrically opposite, but we are more interested in these 2 points here. Now, these 2 points which are closest to the poles on either side, they are called the vertex. And as you can see it, that each great circle track will have two vertices, one in the northern hemisphere and one in the southern hemisphere. And these 2 points are, as you can see it here, vertically opposite, diametrically opposite, 180 degrees. As I told you, that we require the highest latitude and intermediate point, so we should know what is this point in order to avoid, in case that I find that this track is touching, is on my way. Of course, here it is not on your way here, but in case it was somewhere on your way, so you'd be able to avoid it. Now, I just told you that half of the circle is above and half below, and similarly this half and this half. So if you look at it, it's basically this equator has divided this great circle into 4 equal parts of 90 degrees. So you have 90 here, 90 here, 90, 90. Now, even the equator would be divided by the great circle's plane into two halves. One is this side, one is this side. And similarly, you'll have 4 equal parts here of 90 degrees each. Now, I've written down here a little imagination on your part. If you could put one bangle to another, and the centers of both of them were at the center of the planes were passing through it, you will see that half the bangle is above and half the bangle is below, and they are divided into 4 equal parts. Now, this is how it is, 90 degrees here. I've just got rid of the circle which is on the back side of the Earth. So now you have from vertex to wherever it is crossing, great circle is crossing the equator here at O. That is 90. And from equator to other vertex is 90. And similarly, your equator also been cut into 4 equal halves of 90 degrees. And these 2 points, diametrically opposite vertex. If the ship was heading the way I'm trying to show you here. And this is a meridian passing through the ship here. So angle the ship's head makes with the meridian is your course when it is crossing the equator. And as we said that these are 90 degrees apart. So that means the meridians also will be 90 degrees apart. And this angle also, what is formed between this meridian and this meridian is 90. This is arc of the equator. And we know that the D long is arc of the equator. So angle formed here is 90 degrees D long. So two vertices 90 degrees apart. Here the latitudes will be the same in the values, but the signs will be different. And longitudes are 180 degrees apart. From here to here is latitude. From here, from equator to the point is latitude. So latitude should latitudes will be having the same value, but the sign, the hemisphere they will lie, that will be opposite. Now, if I know the position of the vertex, I can find out where this great circle track is cutting the equator, isn't it? That is, at equator, the latitude is definitely 0. So latitude will be 0. And the longitude will be plus minus 90, which is, I've just, as I read this thing, I've just put it as D long here. So you can always find out the position where the great circle track cuts the equator. And you have a triangle, something like this. I've got rid of rest of it. And what we have got here is a spherical right angle triangle. Spherical right angle triangle is one which is made by the intersection of three great circles, and either an angle or a side is 90. Now, this is the latitude what we just talked about. So this side would be 90 minus latitude. From pole to equator is 90. This side is 90. This side we have already said that the great circle has divided, or the great circle track has divided the equator into 90. So this side is definitely 90. And this is the course. So now we have got this triangle which I just showed you earlier. And the spherical triangles are solved using Napier's rules. And as I said that either angle can be 90 or side can be 90. I'll just be dealing with the angles 90 today. Side 90 I'll discuss with you later. Now, how do you go about solving this, and how do you make your diagram for Napier's rule? You'll excuse me that I will be repeating this because I want you to understand it properly. You don't have to mug it up and remember it. And once you have it in your heads there, you will make no mistakes. I have written down here angles are made of two sides, always. Of course, when I talk about the side 90, a side has got two angles on its sides. So I'm not talking about the side 90 here, I'm talking about angle 90. And I make a cross like this and bisect the top portion with a line there. And start off with the two sides what make the angle 90. So the first things what I write on top are the two sides what make the angle 90. So here NC and NO is making 90. So I write those values there. So I've straight away written down 90 minus latitude and 90. Now opposite NC, here we write down what is opposite NC. What is opposite NC? Cos. So I write down 90 minus whatever is opposite NC. Similarly here, I write down what is opposite NO. What is opposite NO? Angle C. So I will write down what is opposite NO. Here 90 minus. Yes, 90 minus angle C. And now out of the 6 elements of the triangle here, including the angle 90, we have used 5 of them here, including 90, and only one is remaining, and that is what we write down here. The remaining, we write down, remaining was OC, I write down 90 minus OC here. And it is solved using this formula, sine middle part, cos, I have written down O boldly because you can remember cos has got O, you use opposites. And similarly tan has got an A, you use adjacent. Very simple to remember, cos, opposite, tan, adjacent. Now this is something which is coming, this is not there in your books, and you will excuse me that I'm doing it like this. Maybe my peers also will not agree with me, but I just want to show it to you mathematically. I just want to say that angle here is 90, here it is whatever it is here. So I'll just try to show it to you mathematically. During my lectures, I'll come up with quite a lot of stuff which might not be there in the books, might not be not appealing to everybody's senses. But if I can prove it mathematically, then I think I should be doing it right. So I am going to be solving for course at the great circle, that is this angle here. And if you look at it here now, I'm solving for this. And I know NC is 90 minus latitude, and NO is definitely 90 because from pole to equator is 90. Now I have to find out this. I can use this as the middle part, and these two sides will become my adjacent parts. Adjacent is the one which is touching the part what you have started taking as a middle part. So just touching each other is adjacent. And I can solve it with this formula here. Adjacent. Tan is adjacent. That's the middle part what has come up there for you. And adjacent and adjacent. I have written it down here, middle and adjacent for you. And I use the formula adjacent. I put the values here. I have taken as a sine of middle part, NO, tan of adjacent, NC, tan of 90 minus cos. I put as sine 90. NC is 90 minus latitude, and tan 90 minus theta is cot theta. Sin 90 is 1, 90 minus theta, as I said, is cot theta, cot theta. So just transporting it here, 1 by cot theta is equal to cos. 1 by tan is 1 by cot is tan, and tan is 90 minus latitude, 90 minus theta. So I've got cot 90 minus latitude is equal to cot cos. I can remove cot, and cos is 90 minus latitude. So the course of great circle, what the great circle track makes at the equator is equal to 90 minus latitude. Now, next I will be solving for angle C, angle what the great circle track makes at the vertex. Now I have got to solve for this. I know these two. I use this as the middle part, and now these two have become opposite. So I'll be using this formula of cos opposite. That's the middle part. What has come up here? Opposite, opposite, and this formula. I put the formula there, and I've got sine 90. Cos 90 minus theta is sine theta, and cos 0 is 1. And 90 is 1, 1, 1 by 1. So sine 90 is 1. So this angle should be 90. So at the vertex, the track makes an angle of 90 degrees. As I said, this is not there in the books. This is out of my hat. I remember it like this, so you can see it here. So we have this angle also. It is making an angle 90 degrees to what I have written down, that is to the north. And what your course what your line makes with the north, that's your course. So your course here is going to be either 90 or 270. Now you see, if I just had to have written down similarities here, we knew that this was 90, this was 90. And now if you look at it here, this is 90, this is 90. So this course is definitely equal to this side. So this is, I'm just talking about the similarities here. If suppose this side is equal to this, and this side is equal to this, then the third should be equal to this. Similarly here, what I have drawn here, this is the latitude, and this is the angle what it is forming. The great circle track is forming with the equator. This we already talked about is the D long here, arc of the equator contained between these two meridians. And if this angle is 90, then definitely this angle is also 90. And if you look at it the way I talked about the similarities here, this side is equal to this side, this angle. This angle is equal to this angle, so this side should be equal to this angle. So here what I have done is angle NOC plus this is 90. Now NOC is 90 minus latitude plus latitude is 90. Now, so here I have found it out that angle at the track will be equal to latitude. So now knowing the position, last we talked about knowing the position, we can find out the position of where the great circle track cuts the equator. Here I have just added it up. If you know the position of the vertex, you can get the course. As we just saw, course is 90 minus latitude, or the angle what it makes with the equator, which is equal to latitudes. So this is important for you to remember for the principles of or the basics of great circle. You could be asked a question on this, which I'm just trying to show you here, because this is not the question. This is just an explanation of vertex. Again, as I said, it is from my head. It's not there anyway, but I think it will help explain it to you. And these figures have been exaggerated a little bit. They're not in proportion because I could not be drawing better than this here. As I said, the vertex here on top. If you look at the ship which is going here on this track, heading like this, the next position she's come here. If you notice that when it's following this track, its north component is increasing and its easterly component is reducing. And is more towards the north, and east. And angle the great circle track makes at vertex, we just calculated it mathematically, was 90 degrees. And what is 90 degrees to north? What it is east and west. So your ship course here would become east or west depending upon which way you're going. Here I am going easterly, and then from here I'll turn curve and go westerly. If I was doing the other way around, it will become easterly. So at vertex, your course becomes either east or west. Now this is the question what I was talking to you about. A question can be put up to you here. This circle crosses the meridian longitude 90 degrees west with a course. Of course, he is not giving me any indication it is equator or anything. I've just left it out here. But what next is talked about at crossing the prime meridian. The prime meridian is 90 degrees from here. So longitude is 90 degrees away. And we just saw that the vertex is 90 degrees away. So we assume that this is vertex. So he's asking me what is the course and latitude at the crossing of the vertex and the position of the southern vertex. So anyway, this northern side I already know the longitude. Now the latitude we just saw was, and here the thing is I have missed out, omitted equator, because maybe I'm just trying to test your understanding of great circle here. The longitude of the first vertex is 000, prime meridian. And what is the course here? I am going easterly, then it will turn westerly. So it will become, your course here will become 090, and then it will come to what do you call west. And course at the equator he has given it to me is 90 degrees, and we know that course at the equator is 90 minus latitude. I can get my latitude, which is 60 degrees north, and the other vertex 180 degrees opposite, 60 degrees south, and longitude is also 180 degrees opposite. If it is 0, it'll be 180, or I can just add 90 or minus 90, because from equator to one vertex is 90. Either way, so it is your longitude of vertex is 180 degrees. Thank you very much. I'll continue from here with the solution to vertex. Thank you for being with me. Have a good day.